Okay, here's part 2. So page 43. So I have a little chart here to kind of split this up. Maybe if you like graphic organizers, this will help you. So when f is, right, when f has a maximum, and maximums typically tend to look like this, right? And this is the maximum point. F prime is equal to 0 because at that high point, the slope of the tangent line is 0 because the tangent line is horizontal. And f prime is slope, right? So slope is 0. And we have a sign chart, or I provided you a sign chart showing how to the left of my x value it's plus, and to the right of the value it's negative. So typically that's what it'll look like. And then when there's a minimum, which looks like this, right? My slope is also 0 because the slope of the tangent line is still going to be 0. But then if we're working with a sign chart, the sign chart to the left of my x value is going to be negative and to the right is going to be positive. And I like drawing basically what's happening. If something's plus, it's going up. If it's minus, it's coming down, right? If it's minus, it's coming down, and then if it's positive, it's going up. So that kind of depicts what's happening. Okay, so when f is a maximum, the second derivative is actually going to be less than 0. Okay, because the second derivative determines concavity. So when you have a maximum, your graph tends to be concave down, right? If you look at my little maximum there, that is concave down, or a frowny face. And then for my minimum, the second derivative is greater than 0. It's positive, which means concave up. And if you look at the minimum, it looks like a happy face. And it is facing up. All right, so increasing. When f is increasing, then f prime is going to be greater than 0. And greater than 0 means positive. And to simply, or to explain it in an easier way, basically, my derivative is going to be above the x-axis because those are all positive values for y, right? For decreasing, when f is decreasing, my derivative is negative. Simply put, below the x-axis because all my y values that are negative are below the x-axis, or the bottom half of the coordinate grid. Okay, so if I continue, concavity, when f is concave up, I'm just restating what I stated earlier. F double prime is greater than 0, which just means it's positive. Right? And if it's positive, that means concave up. And then concave down, when f is concave down, my second derivative, again, is negative. And negative just means concave down. All right, point of inflection. A point of inflection is when the concavity of a function changes from up to down or down to up. So I provided with 2 sign charts. Okay, I'm talking about this right here. And I provided you with 2 sign charts that determine, oh yes, my first one, I go from plus to minus. So whatever point that would have been, whatever x value that would have been, would be a point of inflection. The second sign chart changed from negative to positive, So again, it's a point of inflection. If I ever have a sign chart that's positive, positive, there is no point of inflection, or I have a longer sign chart with more critical values, positive, positive, negative, positive, then there will be 2 points of inflection there, but not 3. Okay. Critical points, I remind you, critical points are where the derivative is equal to 0. So my slope is 0, right? Or where my derivative does not exist, which means that my original function is not differentiable at that point. And if it's not differentiable at that point, then that may be a critical point. I might have maximums and minimums to either side of it. Okay, so this is just an organized chart. Remember, increasing, we're going like this because we read graphs from left to right, and decreasing, we're going like this. Associate increasing with being positive, and associate decreasing with being negative. That'll help. And then again, concave up looks like a happy face, and then concave down looks like a frowny face, right? Okay, and also concave up, associate that with positive, and concave down, associate that with negative. And a happy face is positive, right? And a frowny face is negative. Okay, so example 6. Let f prime of x equals 4x cubed minus 12x squared. And there's 4 parts. A, identify where the extrema of f occur. B, find the intervals on which f is increasing and decreasing. C, find where the graph of f is concave up and concave down. And D, sketch a possible graph for f. So, A, we're identifying the extrema. That's going to bring in the first derivative test. And then B, we're going to figure out where the intervals are on which f is increasing or decreasing, and we'll use the first derivative test for that as well. C, find where the graph of f is concave up and concave down. We're going to use the second derivative test for that. And then D, we're just going to try to sketch a graph. All right, so for part A, I'm identifying the extrema. In order to do that, I need to derive. But if you look at the problem, they already derived for us, right? The function is the first derivative. They're so sweet. Oh my god. So you take your function, which is already the derivative, set it equal to 0, and figure out what x equals, or what are the possible values of x. I see that they have a greatest common factor of 4x squared, so I'm going to go ahead and factor that out. When I do, I'm left with just one lonely x and minus 3. So according to the zero product property, 4x squared equals 0 yields x is just 0, and x minus 3 yields x is 3. So these are my 2 values. Okay, so I'm going to make a sign chart, and I'm going to use my 2 critical values, and they are 0. Gosh darn it. I always do that. They are 0 and 3. So I need test values. My test values have to be to either side of my critical values. So -1, +1, and 4. So those are going to be my test values. And now I'm going to plug them in to my first derivative, right? So, which is all I have anyway. Correctamundo. So I'm going to plug these suckers in, and I'm going to see what I get. All right, so I plugged them into my derivative, and I got -16, -8, and 64. So, to the left of 0, it's negative. Between 0 and 3, we have another negative. And then to the left of, or to the right of 3, we have a positive. So here, I have 2 negatives and a positive, and I'm supposed to be figuring out where the extrema are. The extreme values are going to occur whenever I have a change in sign. So let's see. This is just going down. And then this, to the right of 0, we're still going down. So that's out. To the left of 3, we're going down. And then to the right of 3, we're going up. Ooh, so look at that. I have a maximum. Or sorry, minimum, my bad. I have a minimum at x equals 3. At x equals 0, I don't have any extreme values. So to answer my question, I would just say minimum at x equals 3. And that would be part A. Notice I don't have the original equation, so I can't plug it in to get a point. I mean, you could do the antiderivative, but it's actually not enough information to do that yet. B, find the intervals on which f is increasing and decreasing. Now the thing with B is, I actually need the sign chart from A. So let me copy that. All right, so using my sign chart that I did in A, I can figure out the intervals on which f is increasing and decreasing. So from negative infinity to 0, this function is decreasing. But then from 0 to 3, it's also decreasing. So it would just be a lot easier to say that from negative infinity all the way to 3, this function is decreasing. And then beyond 3, this function is actually increasing. So from 3 onward to positive infinity, this function is increasing. So because it's plus, right? So I'm just going to go ahead and write that. So f is increasing. Notice I'm talking about f. Okay? They wanted to know about f, even though we started off with the derivative. F is increasing on 3 to infinity. And then f is decreasing. It doesn't matter which one you write first. On negative infinity to 3. You never include infinity and negative infinity because we don't even know where they're at. For increasing and decreasing, it is okay to include the intervals, the numbers, like 3. Usually for concavity, we use open intervals. But for increasing and decreasing, we can use closed intervals. Either way, all books say something different. So, all right, C. Sketch a possible, oh, where's my C? I'm missing C. Give me a second. All right, C. Find where the graph of f is concave up and concave down. For that, we need the second derivative. So they gave us the first derivative. We're going to derive again. And I'm going to take my second derivative and set it equal to 0 and figure out what are the possible values for x. I see that there's a greatest common factor of 12x, so I'm going to pull that out. I'm going to factor it out, and I'm left with a lonely x there and a 2. So according to the zero product property, 12x equals 0, so I get x equals 0. And then x minus 2 equals 0, so I get x equals 2. So I make my sign chart. And I'm going to use my critical values, which are 0 and 2. And then I'm going to pick values in between, or test values to either side. So let's see, negative 1, 1, and 3. Right, don't want to make it more complicated on myself. And now I'm going to plug in these values into my second derivative. All right, so I plugged in my values to my second derivative, and I got a plus here, a minus here, and a plus here. So looking at this, right, plus going up, and then minus, so I'm coming down. And then for the 2, I'm coming down because to the left of it is negative, and then to the right of it is positive, so I'm coming up. So basically, here I have a maximum, and here I have a minimum. Okay, that's how I like to do it. I just like to draw it out, basically. So let me write that down. Max, min. Oh, wow, I totally forgot what I was doing. I thought this was the first derivative test. I'm on crack. So F is I'm supposed to be looking for concavity. I'm so sorry. Please don't let this confuse you. Concavity. Concavity is way more straightforward. A plus means concave up. I thought I was doing the second derivative test. I mean the first derivative test. And a minus just flat out means concave down. So from negative infinity to 0, we're concave up, and from 2 to positive infinity. So these are my intervals where I'm concave up, and then I'm concave down just here in the middle from 0 to 2. And then you would just write that down. All right, so there's my written out answer. F is concave up for negative infinity to 0 and 2 to infinity. And then it's concave down from 0 to 2. And see how they're open intervals all the way around. All right. Next, C. Sketch a possible graph for F. All right, so I'm going to actually use all the intervals from the previous answers. I'm going to write those down. All right, so here's all the information we have gathered from A through C. A told me that there was a minimum at 3. B told me that the graph was increasing or decreasing from negative infinity to 3, but then increasing from 3 to infinity. C told me the concavity of the function. It's concave up from negative infinity to 0 and then 2 to infinity. But then in between, it's concave down. So we need to translate this into some kind of graph. Okay, best way to start probably would be the minimum at x equals 3. Now this is a sketch, so it doesn't have to actually be perfect. Answers will vary. And you could put these anywhere you wanted. It just would have to actually look like the information that is being said here to us. So the minimum being at x equals 3, I can go ahead and make sure I label. Okay, so I don't like that one. It's too close. So there's 3. And then look at your intervals and see what other numbers you're using. I'm using 3 again, right? And then I'm using 0, and I'm using 2. So it's kind of like, all right, so something's going to happen at 0, right? Something's going to happen at 2. And then something should happen at 3. Okay? So 3 is a minimum. You can pretty much place that wherever you want. That's the whole point of a sketch. So I'm just gonna, right here, this looks good to me. It's gonna be a minimum. So remember, it's gonna have to look like this somehow. From negative infinity to 3, this function is decreasing. So it's gonna be going like this somehow. Okay, so from negative infinity, and this is negative infinity, right? And this would be infinity. From negative infinity, this function is somehow just going down. Okay, that's just there for right now. It's not my final graph. It's not going to be a straight line. And then from 3 and on, it's increasing. So something like that. Okay? Concave up. It is concave up from negative infinity to 0. So this has to look like a happy face, right? Happy face. And then it's concave down from 0 to 2, so that's going to have to look like a frowny face. All right, so from negative infinity to 0, it's concave up. So let me go ahead and make this part of the graph concave up-ish, concave uppy, right? Erase this extra stuff here. All right, so that's concave uppy, right? And then it's also concave up from 2 to infinity. So this needs to look concave uppy, right? I hope you're understanding. Just trying to follow the instructions, right? Concave up, concave up. All right. From 0 to 2, it's concave down. So I need to make this look concave downy. And I still have to hold true to the fact that from negative infinity to 3, okay, this function has to look like it's decreasing. So this has to look like it's decreasing. This has to look like it's decreasing. This has to look like it's decreasing. All the way to right here has to look like it's decreasing. Okay, my function does look like it's decreasing, hopefully, right? It's not a perfect drawing, but all of those, that part of the graph up to 3 looks like it's decreasing. That's very important. And then from 3 to infinity, it has to look like it's increasing. And I think it's very clear that it does look like it's increasing. All right. So let's see. I did my min, right? I decided that somewhere around here would be my minimum. I did my decrease, increase, and I did my concave up and my concave down. And there is a sketch of this graph. Is it perfect? No. Okay. They won't always be, but as long as you get the idea. All right. Example 7. The graphs of f, f prime, and f double prime are shown on the same set of coordinates. Which is which? So here I have a graph of 3 functions all stuck together on top of each other. And we have to figure out which one's the original, which one's the derivative, and which one's the second derivative. The easiest and best way I can tell you to do this is identify the degrees, which requires you to actually know functions. So let me write this, degree. Now when I say degree, I'm talking about the exponent. For example, this function right here. This is a cubic, right? This is a cubic function. This is x cubed. The parabola, upside down parabola, just happens to be negative, no big deal. The blue one, that is x squared. And then finally, the straight line, this right here, this is just plain old x. You know, it's x minus 2. Well, actually, it's negative, so it's probably negative x plus 5 or something like that. Right? So if you identify the degrees of each, and then remember what happens when you derive. Okay, for example, if I derive this, what am I doing to the degree of the function? What am I doing to the exponent? Well, you bring it to the front, and then you subtract the 3, you subtract an exponent from the 4, and you get 3. Yes. So what am I doing to the degree? I'm making it smaller, right? When we derive, we're making the degrees smaller. So look at these 3 functions and look at their degrees. The biggest one should be f. This should be f. because when I derive that, I'm going to end up with x squared. So this is f prime. And when I derive that, I'm going to end up with just x. So this is f double prime. There you go. That's one way to do it. The other way is to actually pay attention to these graphs. But I have two more examples that I'm going to actually analyze the graphs on. So I just wanted to tell you about the degrees. All right. Example 8. Use a graph of f prime to sketch a graph of f. So here I have two graphs. They are both the derivatives. I'm going to use the derivatives to sketch the original. All right, so to start off, best way to start off is to look at your function or your graph and be like, okay, my slope is 0 whenever I have a min or a max. Well, these are the graphs of the slopes. So wherever my slopes are 0, right here and right here, that means the original equation had a min or a max. Okay. Whenever my slope is negative, right? Whenever my slope is below or less than 0, below the x-axis, negative, that meant that my original f was decreasing. So if you break this up, that's what I'm going to do. For this section right here, my graph is negative. It is below the x-axis. That's the only little piece right there. So that means that my original function was decreasing. Decreasing. There's another little piece where this function is negative. It's about, let's pretend this is a straight line. Okay, there you go. That's better. So this function is also negative for that little piece. So that means my original was decreasing for that interval as well. And then for the interval in the middle, my function is completely positive. So that means for that interval, my original function was increasing. So now you need to draw something that emulates this. Now, remember I told you think of increasing as positive and decreasing as negative? Well, that helps because now for the first green interval, it's negative. My function has to be negative. For the middle, it has to be positive. And then for the other part, it has to be negative, right? I could be like, okay, so negative and positive, what does that look like? Negative looks like this, and then positive looks like that. Oh, so that's going to be a minimum. And then positive looks like this, and negative looks like that. So that's going to be a maximum. So that's kind of the shape of my graph. Now I get to make it up, of course, because this doesn't have to be perfect. So at 0, right here, I'm going to create somewhere a minimum. Let's make it right here because I feel like it. So I'm going to have something that looks like this. And then at, what is that? Like 9? At 9, right? I'm going to have a max. And I feel like putting it right here. Why not? This is just a sketch. And it's going to look something like this. And then I have to remember, okay, so for this little green section, this graph has to be decreasing. Okay, perfect. There you go. There's my decreasement, right? Yeah, I'm just making up words. And then all the way up to 9, right? This point right here. all the way to 9, my graph has to be increasing. It has to be going up. So I need to make it look like it's going up. And then beyond 9, it needs to be looking like it's going down. So let's see. So how about that? It's going up, right? And put a little curve into it because up here, I need a minimum. I mean a maximum, sorry. So looky. And then for the last green section, my graph needs to look like it's decreasing again. So I need to make sure decreasing all the way to 0, which is right here, and then increasing all the way to 9, which is right here, and then decreasing again at the end. So we're going to go with that. That's my sketch right there. Okay. B, same thing. Figure out all your places where the derivative equals 0 and go from there. So I picked, I made points everywhere that the graph is x equals 0, or y equals 0, sorry. Okay, and then I'm going to go from there by figuring out where is my graph located in those intervals. Is it above the x-axis or below the x-axis? All right, so I did my pluses and my minuses, right? Above the x-axis is a plus, below is a minus. So I'm going to have something that looks like this. Plus, minus, minus, plus. Plus, minus, minus, plus. So that's what it's going to look like. Hopefully, if you remember something from pre-calculus, the original function, you could actually tell what it was. This is cosine. Okay, this is cosine. And if this is the derivative, let's see, what did I derive to get cosine x? Hopefully you're thinking, oh, sine. So my original function should be sine. It should look like sine. All right. So now I'm going to attempt to graph it. And just try your best, right? Doesn't have to be perfect. But let's see. It's going to be increasing from here to about right there. But then it's going to decrease until the very next blue point. Try to hit the points. Do better than I did. And then it's going to increase again, right? Until, well, better yet, let me do that over. Okay, so let's just make small ones, right? So there's my first. And then I'm going to make another one. And like I said, if you remember what sine looks like, right? Should be like that. And then another one. And there you, that's a little big. Pretend it's smaller. And then another one. So I'm not the best drawer on the planet, right? But it should look a little bit like sine. Okay. Moving on. Let's not spend too much time looking at my horrible drawing. All right. Example 9. These are actually two very old AP questions. 9 and 10 are. Okay, so the graph of the derivative of f is shown in the figure above. So that picture is of the derivative. Which of the following could be the graph of f? Okay, start off with the degrees first of all. This is already the derivative. It's a parabola. It's most likely x squared. So the original function is going to be something that looks like x cubed. Okay, so right away, looking at your options, you have two that you can totally just disregard because these are not x cubed, right? They're just linear functions. All right. Now, here at -1, and at 1, these are where I'm going to have a min or a max. There's going to be a min or max at -1 and 1. Let's just write and. Okay, so to figure out what each one is, it's very simple. I've got 3 intervals now. I split that up. To the left of -1, this equation, or function, sorry, is above the x-axis, so it's a positive. Between -1 and 1, it's below, so it's a big fat negative. And then to the right of 1, it's above, so it's a positive. Okay, well, let's emulate that. Positive minus is like this, so there's a maximum at -1. Max at x equals -1. For 1, it goes down and then comes back up. So there's a minimum at x equals 1. Sorry, brain fart. So I need to look at my function, or functions, my possible functions, and be like, where is there a max at -1 and a minimum at 1? So A, a max at -1. No. B, a max at -1. Minimum at 1. Ooh, we have a contender. C, a max at -1. Nope. This is a minimum. And a minimum at 1. Nope. This is a maximum. And there we go. There's my answer. B. All right. Last but not least, example 10. Same idea, kind of. If y is a function of x such that y prime is greater than 0 for all x and y double prime is less than 0 for all x, which of the following could be part of the graph of y equals f of x? Okay, so we're looking for the original function, and what they did is they told us information about the derivatives. Y prime being bigger than 0, right, means it's positive. Y prime is positive. And when y prime is positive, that means that my original y is increasing. So right now, I need a function that is increasing for all x. That means everywhere. There is no part that's decreasing. Y double prime is less than 0. That means that y double prime is negative. And when the second derivative is negative, my actual function is going to be concave down. Concave down. So now I have 2 criteria. Oh, and for all x, sorry. That's everywhere. So I have 2 criteria. Y is going to have to increase, and it's going to have to be concave down. So let's see. A. Okay, definitely increasing. But it's concave up. So no. B. Definitely increasing. And it's concave down. Everywhere, right? Looks like a little bowl. Whereas A looked like, sorry, an upside down bowl. Or A looked like a right side up bowl. Or a happy face and a frowny face. So B might be my answer. C. Oh no, this is decreasing. So let me not even bother. D. D is going up and then coming down. It is both increasing and decreasing, so no. E is strictly increasing, so we're good there. But oh wait, it's a happy face over here and a frowny face over here. So no. So B is definitely my answer. All right. A lot of things to learn for curve sketching. Or figuring out derivatives from the original or the original from derivatives or information. All right, that's it. Do your homework.